不是选择上面，还是说叫他的，然后再看要谁。哎，我找了什么？七了，我知道，然后他有些没有，就是
相当于是 S A 的那种，就是
他这样，但哪没看见？然后他就给我搞到去一个俄罗斯了。
Okay, I guess we'll get started. There'll be a homework that will be turned out. Review your notes. Also, I have another research meeting that's going to come on the March 9th through 12th period. And another VLSI tutorial there to make sure we get use of the class. Hopefully that will be getting more into layout. We did most of the schematics last time. All right. Yes.
When will the homework be due? Because you said it's.
I'll hand it out next time.
When will it be due? When will it be due?
I haven't decided yet because I haven't made it up yet.
Okay.
I'll decide how hard it is. Okay, so we have been talking about NMOS. And as we said, it was requiring a special doping step, which is called depletion mode load, and depletion mode implant. And its purpose is to make a pull-up device. It's still an NMOS device, even though it has a depletion implant. And we connect the source to the drain. It's still an NMOS device, and electrons flow from the source to the battery. The current flow in the experience sense is this way. And normally this would be connected to the substrate, and I waved my hands a little bit last time. I said I'm not going to connect it to the substrate. Well, I'll go someplace nearby, which is the ground. That does introduce a small effect, which we'll talk about later. It's called the body effect. And it has to do with the fact that there is some charge that is present underneath the device. And makes it a little different from just connecting things to ground, which we do for the bottom transistor, which we call the enhancement of the device, because if we put the positive voltage on that, it enhances the performance. This shortage connection basically to the source for the depletion mode load then tends to make it just run at some leakage level, nominal value. So this is enhancement and this is depletion. And the sticker here is we basically connect that to ground. And this is then the BGS applied to the E-mode device, which is also equilibrium. The output for that pull down, which is the enhanceable device, would be plus minus source, but now we get a different result for the two transistors. One is E, and the other one is going to be E. And it's also, this is the source, and that's the drain. One of the features of NMOS is this source to drain type of sequencing. When we get to CMOS, the top ones will all have to flip over. The drains will oppose, basically, at that point. We'll show that later. Okay, so we typically ignore current going out and deriving the VTC, the voltage transfer characteristic, which is our only design consideration at this point, is making sure that we get a decent voltage transfer characteristic to get ideal noise suppression. Because once again, a lot of these transistors today, and there are getting to be more of them, although lots of them are now called dark silicon, which you can't turn them on because it's triple fry. This can make more devices than we can actually take the heat out, or the people who believe they're on their battery life. That drives a lot of what goes on in the business today. In any case, we have these tube devices, ones that pull up, the others that pull down. If there's no current flowing into a load, at least until we make the switching event take place, one turns off, the other one turns on. And then a trickle of current will then flow to whatever load capacity sits out here. So that takes place mostly after the switching event. And we kind of ignore that during the calculation of ETC, although we will get around to talking about the dynamics of switching and the timing of it. So again, we have this problem of noise being generated with all these transistors, all switching, all tugging on currents that are all passed through inductors that we choose in this particular picture to ignore. It's a dynamic effect, and the more rapid the switching, the more sharp the waveforms are, the bigger that noise gets. At least for the moment, we're just going to ignore even that problem and just try to make the VTC as sharp as we can possibly make it. So this is the V out, okay? And then we have the VDS for the demo device, which is at the top. And we have the VDS D plus VDS E is equal to the applied voltage, which we call VDD. That's just the voltage equation. Kirchhoff's equation. Now, so what we're trying to do at this point, the other point is that the VGS, or the demo device, with this shorting connection on here is 0. Anyway, the point of this being that we have now a nonlinear load. The nonlinear load has a characteristic that we're almost vertical at the beginning of the coming out of the saturation of the demo device, like this, and it arcs over. Okay, and that's the pull-up's role is to make a nonlinear device. So this whole guy here is no purpose to do that. It wasn't this really one we had before. Demo device is simply suppress, superimpose this curve on here, and at some point we wind up with this. This just sort of tops off here, maybe. And then there may be some additional voltage swings on the input that raise this even higher. So as we use this as IDS now, which is the same for both of these. Okay. And this is our DGS for the demo device. And this is our VDD here. Point being that if we have our VGSE, which is the V in, below a threshold, then the output voltage for this is going to rise. Why? Well, because this is on and that one's now going to cut off. So the voltage will go up. And reaches the threshold voltage. And so this is V out right here. And what we wanted to do with this nonlinear characteristic is to hang around up here longer than we would have with a straight line resistor. So we can get this curve to go out further, and then it's going to roll off as it starts to change its slope. And at some point it hits this magic location where the transition between the active and saturation for the demo device intercepts and lays on. The saturation curve for the emo device, you get that vertical, nice little vertical segment there. And then of course for the, so what do we got here? This is the D is cut off. And our D is active. Let's put it here. And once we, this is the cutoff point down here. Once we come out of cutoff, we're at desaturation. And we're still in D active. And when we hit this point, we're in the sat-sat region. And we said that there was a upper voltage would be high, and a lower voltage would be L. In this vertical segment, we want to try to fall the inverter. Just a name for it, because this will be this little inverter. And subsequent to that, we pass over this VH to VL, VH up here, this VL here. And then we're into the region where the active part of the emo device appears. So it goes into active. So we're still in the saturation mode. And while the curves bunch up as we get closer to the end and this approaches this axis, we don't get cutoff on the other side. And so there is always some tail going off to infinity here. It can converge a lot, but there's never zero. And this one is pretty much VDD because the other device is cut off. And that's the main driver for trying to look for complementary devices. What we would really like to do is get this type of behavior down here where this just goes to zero and the other devices are cut off. So it would be cut off and the D would be cut off. In the moment, we make little examples that we can analyze. Let me call this region up here A, and the set D act is B, and then C was this nice vertical segment where we're trying to set this voltage to be somewhere around VD over 2. Okay, so that's the ideal. And we said last time that with a simple inverter, you could do that. When you start making logic circuits, depending on the series or parallel connection of these devices, and which ones are on and which ones are off at a particular point in time, you may suffer some movement of this vertical segment. And so you have to pick your favorite combination of inputs, maybe half of them are on and half of them are off, calculate what that would be, and then we'll set this inverter. And then it's going to wobble around here depending on what kind of logic circuit you build. You don't want that wobble to get too big, otherwise you'll wind up all the way over here again, or all the way out here. You have no noise in the gate. What this says is that CMOS has a fan-in limit to survive with good noise immunity. I typically like to see it maybe around 4, and no worse than that. That way the square root of the two pull up and pull down resistances would be effectively 2. And we would take this difference here, and we divide it by 2, and then we go over here by 2, and we would just swing around here. Anyway, the V inverter, we set the two saturation equations equal to each other and rearranged it And for the NMOS inverter, obtain the equation that we have the threshold voltage for E plus the square root of beta D, depletion mode to beta E, and magnitude of the threshold voltage for the D mode device, which is parameters can be quite different from BTE, the NMOS process. And the beta D and beta E, we have the same din oxide, Cox is the same, and mobility, so the major carrier for the two channel electrons will be the same, more or less. There's a little dosing difference, so second order they might not be quite the same. Mostly though, it's the ratio of the width to length ratios of these two devices. So we get this width to length for the demo device, width to length for the demo device, and then over here what it is. And you can see that the V inverter, if we make D mode width bigger than the E mode width, this will get bigger and the inverter thing will move to the right, which is saying if we have a wider depletion mode device, it will be a lower resistance, so it gets pull up harder, everything moves to the right. So this goes this way when width of the E mode device is bigger than the E mode device. And then it goes the other way when we reverse that. And so you'll see this move around the real logic circuit, but for the inverter, we can set it then where we want it. And that suggests a kind of a vacuum cleaner role for inverters. If you get into a situation where we'll see them in something called a PLA, or program logic array, where we can't really do a good balancing act, you may want to put an extra inverter in there to clean things up. We call it a vacuum cleaner inverter. To kind of scrape the noise off. You can't do this every single gate. You might have to go several gates not doing that right and then fix it. Anyway, this is what we came to for the vertical segment. And then we made our comments about NANDs and NORs. And when you put two D-mode devices, or two E-mode devices in parallel, their widths add effectively. There's two current paths there, and it's like having double the width of one transistor. And so we put two of them in parallel. The pull down will be twice as strong, and you'll get a 1 over square root of 2 change in this term, not the whole. But this piece that goes after BTE, that would go down by the square root of 2. If you have 4 of them in parallel and they're all on, and move my perspective as much as I can. This difference term here, if I can. Generally what happens, the D-mode device remains fixed in size. We have a series connection of these gates, and we have to somehow figure out how to make the width smaller. But generally, the smallest width we like is about equal to the discernible lithographic minimum feature size, which is usually what we make L. So it would be hard to make with less than that. That results in having to make the D-mode device wider to pull up better. When there's two things, so you have to manipulate the D-mode device with some series connections. Okay, so we talked about noise margin last time, and we'll review all that. What I'd like to do today is look at the different other sections that we can analyze so far. C, of course, A is trivial. So let's look at region B. And that's kind of nice because it comes off of this threshold, the cutoff point, and this thing is exactly VDD out to the threshold point. It's kind of nice, and it's because there's no current flowing in the pull down, and it's all being pulled up. So this would be the D-act, ESAT. This one here. And so what does that look like? Well, we can take the two equations for the D-act and the ESAT. This is IDS, the D-mode device, active region, which we know is that theta D times VGS minus V threshold for these are VGSD, this is VGT times VDSD minus VDSD all squared over 2 as a bracket. And this guy here we set as 0. And the VDSD has to be related to the output voltage, which is different from the VDSE. Now, the saturation we've already written for the E-mode device last time. And that would be beta E, now divided by 2. And then the VGS, the E-mode device, minus its threshold, the E-mode device, all squared. These formulas now is just sort of routine. You should know them by heart. For those of you smart enough, if you're going for a PhD, I usually ask a question about Fick's law. I've seen some of these people come up. I don't know what it is. Huh? You've never seen this derived. Okay, so this is V in. It's not canceled out, it's just V in. This is 0 here. The other thing that we have is, of course, the fact of Kirchhoff's voltage law, which is VDSD equals VDD minus the drop VDSE. And VDSE is the output voltage. We can take that and put it back in for VDSD. Okay, I don't want to have to reach in there and do an arrow there, but that's what we'll do. And the result will be for this first equation, beta D times minus V threshold D minus VDE minus V out, all 2 times VDE minus V out. Okay. And that gets us basically this is 1, this is that, this times that. This, and that one over there has got 2 of them, it's divided by 2. So that's where that comes from. And this is beta E and over 2. Times V in.
Take row,
Yes. V in minus V threshold E all squared. So this is obviously solvable for V out some function of V in. Unfortunately for us, all of our crude approximations make it all into a quadratic equation that's pretty simple. And just doing some little divisions here, the beta E is divided by beta D, and we get E in, E in, minus V threshold all squared, plus 2V threshold D. Okay. And just move this term over to the other side. And minus 2V threshold D times V1 is equal to, now this is all here, is equal to minus VD squared plus 2VD out minus V out squared. In rearranging, we get a conventional quadratic equation, the usual form. Isn't that nice? And it's all quadratic, except it isn't. The real world, everything is a mess. And you have to do it all numerically. But the purpose of trying to understand things, we're making these approximations so you can turn the mathematical plane, feel like you're in control, right? minus V naught squared plus 2 times VDD plus V threshold D, times V out, minus V beta E over beta D times V in minus V threshold D all squared minus 2 V threshold D times VDD minus VDD squared equals 0. And the usual identifications for the Ax squared plus Bx plus C equals 0. The A is equal to minus 1. The B is equal to 2 times VD plus V threshold D. And the C is a little messy. Minus beta E over beta D. V in minus V threshold E squared minus 2 V threshold D VD minus VDD squared. And the result for solving that using the conventional quadratic formula is V out equals, there's a 2 cancellation here, VD plus V threshold D. We've got 2, these cancel out. And then there's the inevitable let's take the plus minus. Which one is it? Have to argue that case. Physics. Math is not going to tell us. There's 2 more terms here, so this I'm going to cheat. Just draw over here. Minus 2 V threshold D VD minus VD squared. Okay, and the question is, what is the sun? Now, we know the physics of the thing is such that we should be coming out at VDD on the V out versus V in. That's what this equation is. Hit the threshold for the EMO device, the threshold for the EMO device, and it should roll off. So there's a point of continuity here between the A and the B segment, and it shows up when V in equals V threshold. So what I want to do is take this equation and set that in there, and so at V threshold E, what should we get? That would be right here. It has to be VDD. Okay? And this is VDD already. And that's the threshold D above it. But it is actually the value. And so what we want to do is to basically cancel that off. And depends on how you actually want to do this, but for example, V threshold D and VDD. Also lost something here. So V threshold V in is equal to V threshold D. So V threshold D, so this cancels out, so that would be gone. You square this, and basically 2 of the terms are there, except for the mysterious squared. And what we want to do is, whatever VDD is, we want to cancel that VD, even though that's negative there. So we would have to put a minus. And if you treat VDD, V threshold D rather, as negative, it will still subtract this from the other VD, and now you get VDD. So this checks. This is the minus sign. Anybody see that? So we now have an equation for one of the segments in here, and it's sort of like what we were doing with the linear pull-up resistor, but now we've got a nonlinear resistor. And this does meet right here, so that's good. And one of the questions might be, what is the slope when it breaks into section C? That, my friends, is probably on the homework. there a kink there? Or is it actually going straight down? Okay. And then the question is, what might be the slope over here? Anyway, then we break into D, which is down here. We know that D is never going to go all the way to 0. What does it do? So if you happen to accidentally be in a business like gallium arsenide, which is often used in a lot of radars, used in automotive radar, places like this, it's not going to cut off, so it causes problems with leakage. So region D would be the DSAT and DACT.
Excuse me, Professor.
Yeah.
With the previous part, earlier on in the class, we chose positive, I believe. Why did we choose, why is there a difference between?
Well, in this case, you have to look at what this is here. So it's V threshold D. All this is going to come down to square root of V threshold D squared.
All right.
So the plus or minus is still an ambiguity whether you have a minus or a plus VD, VTD rather. And so you have to make it minus in order to cancel it out, or it's just not. See, now the other one we were down here, this one is up here.
Okay, so we were talking about a different part
A
earlier.
different intersection. But you gotta, figure out how to test it, make sure it's doing the right thing. This one turned out to be easy to do. So just one more little exercise like this, we'll do region D. Also because it's sort of homework-like, something you can do with your brain. Although I suppose some people can do it with MATLAB. Check your work. But I like brain type work better. So this is DSAT. Well, DSAT would be beta D over 2. BGS with D mode device minus the D threshold of the D mode device, all squared. And this again is 0, which makes that really simple. And then IDS E ACT, which is more complicated formula. And then this is squared here. Over 2. But actually what I'm going to do is I'm going to factor out the EDS. So I'll put it there. And now the junction where we go from C to D is such that IDS D SAT equals IDS E ACT. That's the point of transition. And we can set these two equations equal to each other with the appropriate simplification there. And of course, this one is the in. That one is out. And away we go. We get beta E. V in minus V threshold E minus V out over 2. V out equals beta D over 2. V threshold D all squared. It's actually a simple looking equation we had earlier. And rearranging this equation to make it look more quadratic-like, V out squared minus 2V in minus V threshold E is the coefficient times V out, the new term, plus beta D over E times V threshold E all squared equals 0. And the A in this case is 1, the B is minus 2 times V in minus V threshold for E mode device. And C equals beta D, beta E, and V threshold D all squared. Leading to a relatively simple formula for the fall off. And that would be equal to, and the 2's will cancel, I'll just write 2 here anyway. V in minus V threshold E, plus or minus square root of, and then we get 4 V in divided by 2, 2's go away, 4's go away. And we get a relatively simple expression in which V out is V in, minus V threshold, plus or minus the square root of V in, minus V threshold D, all squared, minus V D, and so what we might be tempted to do, because we still got the sign ambiguity in here, which is related to here we are on this characteristic. Here's the top. And here's our pitch point. And then here's our here. This is the threshold. And so this is one threshold down, positive number. So this would be, well, we could call it plus V threshold D because it's a negative number. It actually moves down here. So that's where that point is. Exactly if this is the inverter, we just subtract off V threshold T, and this is the one we want to slope. And that tells us this over here is the inverter minus that V threshold D. Low versus high. Okay, and now we got this thing tailing off, starting here, and the temptation will be, let's go look at V in equals V inverter, which would be, you know, the square root of a bunch of stuff. Unfortunately, what happens is that this guy over here turns into 0. Do that. So we can't tell its size. Unfortunately, that didn't work. Unfortunately, VE equals VO rather. VO equals just little baby E, V threshold E rather. Plus or minus 0. So you can't tell a sign. That's 0. So what we do is we have to notice that what we want here is a descending slope. We want the thing to be coming down. So one possible way to look at that is to look some short distance away from where V is equal to V inverter, and this thing will be 0, and then we'll want it to be descending down. So instead, pick some small difference between V in and V inverter. And then V inverter, sorry, V out is equal to this epsilon plus V inverter minus V threshold E plus or minus the square root of epsilon, which is a small number, plus V inverter.
Move it up, please.
Yeah. Minus V threshold E all squared minus beta D all threshold D squared. Okay, and then what you want to do is expand this around small e or epsilon. And then pick the sign so it's going down. So I'm going to skip a step here and just write that down. When I do that, this is approximately equal to epsilon plus the square root of beta D to beta E times V threshold D. Plus or minus, okay, here's the thing we're worried about. It'll be square root of 2 epsilon, which is getting small, but it's still there. Square root of beta D, beta E, and 2 to V threshold D, times 1 plus 1/4 of epsilon over 4 times the square root of A Z over A B. B threshold D. Close parenthesis, plus other terms. And clearly, in order for this thing to be coming down, we've got to pick the minus sign. There's the next term up here, which is the next one of the highest, the next magnitude here. So that is a minus, so pick minus. We go back to the original solution, circle. The original one. Oh, this point, I kind of lost it. Pile, and Weaver equations. Here's the minus sign. By the way, that was B threshold. Okay, so that's a technique for trying to figure out which sign it is. You just look for, you know the slope has got to be going down. And you just pick the sign, so yeah, that fits in this figure is going down. Please do that. But it never goes to 0, and that's the point of deriving that segment. Is it just never goes all the way to 0, and so you never reach cutoff where you cut this guy completely off. Well, I mean, the reason why you're not doing it is you made it leak anyway. If you dope it so it'll leak on, right? If you really want this to cut off when that one is trying to pull in another direction, then you're going to have to change this whole thing. That whole thing has to change. That's where CMOS becomes important. So we finally hit CMOS. But now there's enough motivation as to why would you do it. And when you're doing gallium arsenide, why do you do it that way? Or indium phosphide or any of those other hugely important materials. What is CMOS really all about?
Professor McDonald,
Yes.
could you put that last paper real quick, the one that had the final equation on it?
Yeah. Find it now. What I do with it. I'm having a little trouble with this. It's kind of easy to hold up to the side. Why don't you come out after class? Sure. What is important to understand the technique? I wouldn't do exactly that on homework or test either. So something like that might happen. Disappear that quickly. Anyway, okay, so our problem is that we have this fixed characteristic, which is sitting up there in the stratosphere, and it doesn't go to cutoff. It's either in the active or the saturation region. To get anywhere with this cutoff, we need to have something where we can get the other device to cutoff. That only happens when we do CMOS and need another kind of transistor to do this. We talked about the N FET, and now we're going to do the P-channel FET. The reason why we started with the N FET, of course, for the electron voltages are higher than most common doping densities in some of the earlier technologies. So the N device is always faster. We would want to use a slow transistor. But as we get to higher doping densities, because our volumes are getting very small, then the two mobilities decline. They're in the toilet, but they get closer to each other. So there isn't any favoritism here. Might as well use the other device. Now with the P channel, all we do is reverse all of the polarities of all the materials. So here is our substrate. The substrate is now N-doped. And we would have a thin oxide as usual. And we would have a gate, metal. And we would use that self-aligned gate to help with the lithography so we can get this edge to be very close to that edge. If that doesn't happen, we get some extra leakage problems around the edges. It becomes more significant when the whole thing is very tiny. And this would go out, and of course you have your box, box. And we'd open open this up and put in our contact metals, which have to be ohmic, not Schottky. In this one over here, we can ground if you want. But now, all the polarities of the batteries and so forth will have to change. So this guy up here, he's got to go with the negative voltage to turn him on. So our VGS for the P-type device would be negative. And then the drain side over here also has to go negative. And that, of course, would be our VDS. Or VDD if you want, VDS is also for the P-type device. And now we're doing this now with respect to having this in ground and this in ground. All the voltages are now flipped. This is P doped here. P doped. And the current, in course of trying to use this device, by flowing negative voltage to the gate, we will attract holes into the channel. And the primary mechanism then will be to defeat the usual diode blockage, which we would have here, facing the other direction now. But with the minus sign over here, this one is blocked. And so no current will flow until we put some negative voltage on it, on the gate, which would then cause inversion to take place in exactly the same manner as it takes place for the in channel. But everything's negative now. All the voltages are all negative. And if we were to plot this IDS for the P mode device and the VDS for the P mode device, it's all negative. We've got our curves running this way, down here. Everything else is the same, but all down here. Got negative voltages, negative currents. Ow. We're going to do that. Well, it's a bit of a trick. I call it the hydraulic jack. We lift everything up with a hydraulic jack. So what happens, so we have all negatives here. Well, we know we would like to use CMOS with just positive voltages. What we can do is we can take the whole structure and jack it up. That is to say, here's our device, here's our contacts here. And I'm going to take this, and this is our point which we declare to be ground. I'm going to lift the whole thing up by putting a positive voltage here. And then make our connections to what used to be ground. So we'll do this. It still thinks that it has this substrate voltage of ground, but I just lifted everything up. And then over here, all these negative voltages will just sit on top of this voltage over here. And so here's our negative battery for the maybe VDD. Minus VDD, but it's now sitting on top of the plus VDD. Which means this effectively is at ground when this is a full VDD. This guy over here generally have a smaller voltage than VDD, negative, propped up by full VDD voltage, so what will happen is it won't be zero, but it will be positive relative to this ground over here. This is big and that's not as big. This is your VGS. So what we have to do is we have to lift the whole structure up, offset everything by voltage, Okay. How do we do that? This was the big breakthrough. CMOS possible is called InWell CMOS. In InWell CMOS, we have our conventional in-channel doped transistors here. Those are our NFETs. And they would like to be grounded. They would like to have input voltage in, which is positive, or 0, and output voltage should be out, which is positive. And we need, of course, a battery to accomplish all of that. Over here, put this other device in an N-well. And this is, of course, P-doped down here. I will ground this P-doped wafer, or die. And into this, I insert an N-well. I have to do all the ion implantation and diffusion correctly so this doesn't go all the way to the bottom. Usually this is 100 microns or so, but sometimes you fit it to get the heat out better. You have to worry a little bit about this N-well not going all the way to the bottom. But what it does is it has two contacts. Here's our, what we're going to do is build our P-type transistor in here. Okay. This is N-well, so this is P-doped, this is P-doped, this is N-doped. Okay. And we want this to be brought to a voltage which is now going to be at a high voltage because that's what we want to have for our device. And what we do is we put another contact over here on the N-well, and they're both held at VDD. Okay. And that's the VDD offset that we would have had for ground. We would have had ground over there. So this was the source, and that was the drain. That says this is the source, and this will be the drain. The drain for this device wants to go to, again, a voltage which is positive, but looks negative with respect to its N-well, which would be anything be out that we can generate from this sort of circuit. And then the in is going to be here. This V in is either 0 or a positive voltage. When it's a positive voltage, this one will invert, and that will be blocked. When it's 0, it turns out that's enough with this VDD on the other side to have the negative VDD applied to it, and it will fully invert conduction. So this is called N-well CMOS. Provides a well to isolate. And why does that work? Well, we have VDD attached to the N-well. What we're going to do then is we have, of course, this junction here. That diode is in reverse bias and provides isolation between the PFET, which is this guy here, the NFET. And in addition to that, we may choose to use box to provide additional isolation. But this results in having this whole transistor jacked up by the amount of voltage applied to the N-well, which is then isolated from the P-well and its ground connection by positive voltage. Everything is lifted up by VDD, and that's exactly how we make some of the voltages inside the transistor look negative, even though all the voltages that are being applied are positive. It's just that they look negative relative to this N-well. And that provides a kind of a co-integration medium, which has worked for, 35 years, 40 years now, to make what amounts to a less leaky type of transistor, because now where we were unable to cut off the DMO device, it was stuck in this little place in the IDS versus VDS curve space. This is now going to have ability to move around. So when we make our little circuit diagram for this, here is our, what used to be our emo device, but it's now just called an NCAT. It's still an emo device, same transistor, nothing different. So this is all the same as our NMO device. But then we have another device, which is this guy here. And the way we denote, oops, let me just repose. I'm not even paying attention to what I'm drawing. Here's our enhancement mode in channel. Exactly the same as before. And now we do is we go up to this other transistor, whose polarity is shown as more or less the electrons would repel, holes would be attracted into this gate with an arrow on it. That arrow is to the substrate, and that substrate is a VDD. So here's the weird thing. Here's our pull-up, and the end well provides a substrate that is different from this substrate. This one is attached to VDD. Okay, now we got two inputs here. This is what's different. Before, we would just wrap this around and hold it in its mid-operating range, so it would look like a nonlinear resistor. What we're doing here is we're going to actually move both characteristics around. One will go up when the other one's going down by applying a positive voltage. Now this positive voltage is plus VDD here, and this is VDD here. You've got 0 across that channel that is not going to convert. So this one's off, even though there's a high voltage applied to it. Here's your output. Again, we'll assume for the purpose of calculating VTC that I 0 on the output. Later, when we get into charging and discharging the loads, this is clearly going to take a current, where we allow the transistor to go completely through its transition, because its parasitics are much smaller than those of anything that we use to connect the devices together, at least for representative circuits. Now, one of the things we didn't quite catch here, which is what is the IDS? Now, this is IDS here for the conventional N-channel device. Now, which way is the majority carrier going here, whether the positive stuff is all falling in this direction? We apply a positive voltage here, we'll tend to push the holes in the other direction towards this other end over here. And what that means is that will be the drain for that device. And this becomes the source. I.e., where the holes are manufactured, they go to the channel, they pop out, you can buy open the drain. Whereas this guy has always been D here and always source down here for the N-type device. So the SD definitions look a little bit strange. And VDS for the PMO device then would be measured in this orientation. And IDS for the PMO device would be from the range of source here over there. And so that's just a polarity definition, and the IDS down here. It's going in this direction, which I already showed, and then the VDSN is as was shown before, plus or minus in this direction. So V out equals VDS N-type device. Now, this is circuit representation of what the physical design looks like. And while we have the Kirchhoff voltage equation, which says VDD, and if we do the DS for the P, we drop this and equal the VDS for this. Okay, and that's using the D and the S, the orientation of the pins the transistor is shown. Which means that VDD is equal to VDS in minus VDS P. Or, another way to write it is VDS in plus VSD in the opposite direction for P. Any way you want to write the equation. And so when we put them together with this equation, we will take the curve that we showed for our P-type characteristic, which is all down here, okay, and it's going to basically move it over by VDD. Okay, when we do the overlapping of the two characteristics. Also, the VDS, the IDS for the N and the P are in the opposite directions, and so the result is going to flip the current over to the top. And the net result is going to look something like this for a calculation of VTC. So let's put the EVO device to sleep. So he's down here in the cutoff position. And this will be IDS for the N-type device, and VDS for the N-type device. Plotting on top of that, we would take this offset of VDD and shift the VDSP by plus VDD, which will move it over here somehow. VDD. But then the currents are in the opposite direction, which flips the equation over. Now, when the voltage for the EVO device is such to cut it off, the other guy is getting 0 on his gate and has a VDD on his substrate side, and so he thinks he's inverted, and so he goes all the way to the top. So this guy's up here when this one's down here. This is your so this is your P-type device, and this is your N-type. Okay. And now, as we crank voltage into the input, what will happen is this curve will move down as this one moves up. So let me draw that maybe another color here. I'll try to do a red. So as we begin to edge up our VGS in our input, which is VGS in, this guy will start to sneak up. You will still have this little critical transition on that parabolic from here. And the other guy will start to come down. Now, as I mentioned to you before, the rates at which they move were quite spread out up at the top, and so it might move more on the top and maybe a little bit at the bottom. And this will gradually continue until we move to this green state, where this is going to go up here. And he'll go into his saturation. And this is green now, it'll look that green. So this is the third curve I'm plotting here. This is green and black. These two will overlap, and there'll be a range here from V high to V low, in which they will actually just sit right on top of each other. And then, like two ships passing in the night, the next higher voltage will begin to move the P-type device down even further, so they'll come down and go down here someplace. Then the N-type device will have gone all the way up to the top, so he'll be up here, someplace up here. So they're like passing in the night, and when they exactly hit the same point, you get one of these sat-sat regions, which is good. That means we're going to still get our vertical segment in the VTC. So let's see if we can at least sketch what the VTC might look like based on two ships passing in the night. one of these curves is going down, the other one's going up, the VGS route. The VGS for the N-type device is VN. Okay, but the VGS for the P-type device is equal to VD minus that VN, so it looks like it's going down, and the other one's going up. And then this would be our IDS for the N-type device. But superposing the other curves. Now this will be V in and this will be out. This is the voltage transfer characteristic. Let's see if we can schedule. Again, when the EMO device is in cutoff, it's down here and you're going to be nailed to that VDD, which is good. Now, as we begin to move out of it, this curve is still pretty vertical. So you're going to get a lot of that benefit of what I call the Schneise effect, where this goes out, sticks out more than it would have otherwise. But at some point, the curves will begin to come close together again, and you'll get that vertical segment, which is here. This is the E mode, ESAT, DSAT. This one up in here, E is SAT, and that's cut off. And the D mode is active. And that goes up to the B threshold for the E-type device, and all that's the same. What's going to be different is what happens when we come down below that.
Professor McDowell?
Yeah.
Isn't it N and P, not E and T?
Oh, I'm sorry. The EMO device is N, this is P. N. You were paying attention, so you deserve a brownie point. What's your name?
John Rawlinson.
John Ralton?
Rawlinson, Rollinson.
T-O-N?
SON.
You got a brownie point. Yes, because the professor doing wrong things and you're paying attention. You got a brownie point for correcting. I think that's what I want. I'm old, I'm 74, I'm going to make a move once in a while, but this is your opportunity to prove to me that you're paying attention. I'll put out some brownie points. Not quite as nice as a real brownie, but you know, it doesn't take yet. I hope you're not too hungry. Yeah, and so where are we here? We're on this curve point. Well, we're still the P-type act. So what has happened is we've gone basically out of cutoff into the end is saturated. That's this one here. So we've got an A curve, N cut, P act. We've got a B part of the curve, which is N sat, P act. Vertical segment as before is N sat, P sat. Then we're going to go into another segment here. This curve is now falling for the EMO device, the P-type device is falling. Eventually it will cut off. Okay, so when it does, no current will flow. And that happens basically when you are dropping below the threshold for that device, but because that has to be up here someplace, it's going to be DDD minus the B threshold for the P-type device magnitude. And here's VDD up here. In this region in here, the P-type device is now going to cut off. And the N-type device is still in saturation because this guy is going here. Now we're in the active region, sorry, for the P-type, N-type device. So we've gone from cut act to act cut. And then there's a segment in here where we're between this point and the one that's below it. This is our P inverter, which we still have to compute. It'll be more or less along the same lines as before. We're trying to tweak the pull up and pull down strengths so this falls right in the middle. This is VDD up here. This one threshold offset down. We're going to cut off at the top. So now we reach these extremes. We can actually get all the way into these regions. We will cut one or the other two transistors up with a pull up or a pull down. And that's the main beauty of CMOS. You know, when you're thinking about your car sitting in park and fly for a long term, any little leakage that's going on in there, and it turns out it can be a fairly small amount of leakage. Like if you actually can wave a wand around and have your car unlock for you, there's something running in that car. It's sniffing. It's running your battery. So you want that powertrain to be as little as possible. Right? You want that cut off at the top. That's what has been driving this business in this direction. You can't get it in gallium arsenide. It's not get any speed out of it. And I don't even bother. Now, this curve here is the well-known cutoff for the bottom. What is different about this one is that this curve is actually moving around, and it has its threshold voltage negative. It's over here. And there's a 1-to-1 slope here. So this is the difference between NMOS and CMOS, is that this is now a sloped line. This is a 1-to-1 slope. That's a 1-to-1 slope. And go right through the VH, which is up here, and then the VL is down here. Okay. And everything after this now is going to be a lot of equation derivations, so I'm going to quit here. I think what I want you to do mostly to come out of this is an understanding of how we have evolved here for the low resistor pull-ups, which maybe some people think looks like an amplifier. I don't think it makes a really good amplifier, but people do make amplifiers out of it. And then you can get into NMOS. That's still got a kind of a crappy transition between input and output voltage. And for digital purposes, it's got great because it has a vertical segment. Who would want that and would do an amplifier? So, not too good. But it's really great for making logic, and that's where it's been successful. So that will be it for today. And I want to get your attendance sheet signed.